Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In the previous section, we talked about linear voltammetry, linear scanning voltammetry. That means potential was linear increase or decrease, and then we measure the corresponding current. And then we plot the potential or the cell voltage against current. We got the polarization curve. In this section, we're going to discuss about how the application or implementation of the polarization curve or the EI curve. So over here, we're going to talk about what the voltage loss in the polarization curve, why the potential will change, what the key component inside. Let's see, we use a fuel cell or the battery, the cell voltage against current curve as an example. Within here, when we change the current, the cell voltage will decrease. So why the cost decrease? Actually, there's several possible reasons. If it's an ideal case, the cell voltage should remain at the same voltage. Doesn't matter what the current will be. Always keep at the ER, this cell voltage. But in reality, as you go to higher current, the cell voltage will be decreased. That's the case for fuel cell or battery. For the other case, like electrolysis or electroplating, then the situation changed because energy was supplied from externally add into the electrochemical system. So as the current increase, actual cell voltage will be also increased. But this case is you release energy from the electrochemical system to external environment. So as the current increase, the cell voltage will be decreased. Why is the cell voltage decrease? There's several factors affect that. That will be including the ER. This is at the equilibrium potential, or we call it open cell voltage. And this one, the activation over potential, ohmic loss, and the concentration over potential. There's several factors which will be reduce the cell voltage from the reversible cell voltage here. The activation over potential is due to electrochemical reaction, like activity at the electrode surface or the area of electrode surface will be affected on the voltage loss due to activation over potential. Internal resistance Ri will be cause the ohm voltage loss, and then the concentration over potential will be affected on the concentration over potential here due to the concentration gradient between the bulk and on the electrode surface. Those three factors we can plot something like this, and then the activation over potential will be part of this, and then the IR over potential and the concentration over potential. For the activation over potential, we actually you can this one can be derived from another section called kinetics. Electrokinetics probably going to explain this one more detailedly, but we just get this result. Activation over potential, the voltage loss can be plotted as a function of log I, and then this exchanging current density, and alpha is charge transfer coefficient. So this one can be abbreviated as A minus B. The A is this term and the B is this term. So if we plot the cell voltage loss delta VAC against log I, it will end with a linear plot. And then the intercept at the 0 here will give you the exchanging current density. And then the slope will give, you can calculate the alpha F. Usually the activation over potential will be due to the electrocatalytical activity will be active or less active, will be effect on the activation over potential. And then the internal resistance here will be effect on the potential. You can see the cell voltage at different internal resistance. Then the actual slope of this EI curve will be changed. This is quite significant if you really see, if you want to control at a given voltage. For high resistance, you might end up with a current something around here. But if you reduce internal resistance, you might end up with a current much higher this part. So, and for the PEN fused cell, actually, right now what they're doing is they try to reduce the thickness of membrane, therefore increase the output current at a given cell voltage. So each one, the activation or potential on internal resistance or concentration or potential, they have their own different behavior as respect to current. You can see the activation or potential that had a significant increase. The voltage loss due to activation or potential is at a lower current density change very large. At a higher current, actually kind of tape off. This is because logarithm function caused this. And then for the internal resistance, it's kind of linear behavior because this one, the ohm resistance, is a linear only function as I, since the Ri will be a constant. And then the concentration over potential at a lower current density is not change a lot, but the most significant is at high current density, where the close to the mass transfer limiting current, then the voltage loss increase substantially. You can see from the mathematical, when the I close to IL, the denominator nearly zero, so this term becomes infinity. So how we can use this one to make a Tafel plot? There's another application. If you know all the overpotential loss, you can make a correction for the Tafel plot. In many experiments, we measure the current against voltage or current against electrical potential. We got this this series, and then we try to make a Tafel plot. And this one kind of sometimes puzzles us because it's it's a curvature. The current is a curvature. How we can draw a linear line? Because Tafel plot tell me the voltage is a linear against the logarithm of the current. This is in the log scale over here. So it depends on which area you choose. If you for this one, because inside here the electric potential, not only the activation or potential loss, but also had internal resistance. That may be the wire, the cable you use, or the electrolyte, the conductivity, or the working electrode too far away from the reference electrode. All this will be affected on the internal resistance you get. So over here is a kind of continual curve. So it depends on which potential region you try to do the curve fitting, try to make it a Tafel plot. You might end up with a different slope. The alpha will be different. But actually, for a given electrochemical reaction, there's only one Tafel plot. What happened is that because the internal resistance caused this problem, so we can make a IR corrected Tafel plot. So this one we call the IR correct Tafel plot. We move the IR from the right hand side of the equation to the left hand side, and then we plot the E plus IR against log I. Then you got the green dotted line, the data. So it's much linear compared to the blue data, which not making IR correction. So sometimes if your experience data show this behavior, usually curvature behavior, usually because the internal resistance you haven't corrected. This usually in the potential state or the fuel cell test station or battery test station, usually they had a function to measure the internal resistance. And then if you got the Ri, you know the Ri, then you can make it a IR corrected. Sometimes the program itself will make a internal resistance corrected. So from here you can draw a line. It's much behavior much better for the making a Tafel plot. But at high current density, you can see the data still had a cross over here. So this one means we had a mass transfer correction also. Because at a high current density, here is close to mass transfer limiting current. So there will be cross altogether here. So you can see over here, if there's a lot of noise during the measure data, then you might end up with different kind of Tafel slope here. But if you make a IR corrected, so you might have the chance to get a better plot over here. But at a high current density region, it's still a kind of a variation. There's a lot of noise here since. But all this one because the mass transfer is not corrected. So if we make a mass transfer corrected, that means the limiting current you can read actually from here. If you the blue line origin data, this probably will be the limiting current. You can read here the number of here. You substitute inside here and then make a correction here. Then you got the red line data, and then you might get a better fitting in here. Over here, I just intentionally make it assume there's a big noise in the data, but you still can make a reasonable Tafel plot with internal resistance correct and mass transfer corrected. So there's the EI curve you can make it out of this. When you can, if you make a Tafel plot, then you got some kind of kinetic parameter. You got such as exchanging current density in alpha over here. There's other kind of application. This I quoted just from this paper. This one they as a fuel cell, but they use a different Nafion membrane. Each membrane they have a different thickness. The Nafion is a separator to separate the cathode and anode. And then the Nafion, the 117, 115, 112, the different thickness. So the internal resistance will be different. And this is the data, the cell voltage against current. This is the series, the cell voltage against current. And then the black dot is a cell power against current here. The cell power is equal to the cell voltage times the current, give you the power here. Over here, they use this equation to do the curve fitting. And in the literature, actually, there's a different kind of equation they can use to do the curve fitting. But here they use this one. They only consider internal resistance. Over here, they also control the mass transfer parameter here. So they end up with for different Nafion membrane, they're able to curve fit it and find out the internal resistance and then corresponding the kinetic parameter here. You can extract from the curve fitting. That's one typical application for the EI curve. The other application for the EI curve, this from this paper. Over here for the vanadium 4 plus oxidized to vanadium 5 plus. This species, they might go through different reaction paths. For instance, the reaction path 1, they might go from the 4 plus oxidized electrochemical reaction oxidized into this species, and then go through a chemical reaction and then become the 5 plus. This one is the path 1. We call the ECC process. That means electrochemical and a chemical and a chemical process. And this is the equation. This is not a point here, but if you're interested, you can see how they derive this equation. And then they possible go to the path 2. That means they go through this reaction path from here to here and then to here. So this is the path 2. It's a CEC process because they go through the first chemical reaction, electrochemical reaction, then the chemical reaction. So chemical reaction, electrochemical reaction, and chemical reaction. The last one will be the path 3 is a CCE process because they go through the chemical process, electrochemical process. So they derive to the rate or the current against the potential, end with this kind of final equation. And then they can plot the Tafel plot. Over here, slightly different is the current logarithm current against voltage. They plot in this manner. So from here, you can, if you run the experiment and then fit in, see which scenario will be best fit, and then you can decide your reaction mechanism. There's another application from the linear polarization curve. For instance, you can put a reference inside the cell, the vanadium redox flow battery cell, and then you can make measurement for the negative electrode, and then you run the linear polarization curve. So from 0, go to the more positive side, then the vanadium 2 will be oxide to positive 3. Or you can go to the more negative direction, the potential, then you reduce the vanadium 3 plus to vanadium 2 plus. You end up with this polarization curve. If you measure the positive electrode against the reference electrode, sexual calamine electrode, then you can run a scanning from this direction. You end up with this curve, and then you start scanning the electrode potential this direction. You end up with this curve. How this curve will look like? First, if this is the on the top is the oxidation current, the current will be positive. On the bottom will be negative. Current will be called the reduction current. And then at the 0 current is the rest potential or the equilibrium potential for the negative electrode or the vanadium. And then the other will be on the positive electrode. And then the potential difference between this electrode will be the cell voltage. We call the OCV, open cell voltage, because current is at 0, this condition. From here, we can see for a given current here, then on the negative electrode, in order to reach this current magnitude, the potential just need to shift slightly. We call the eta A, the anodic over potential. And then on the positive electrode, in order to reach this same current density, the potential has to shift much larger portion, the anode potential and anodic potential. You can see. So this one gives you indication in the positive electrode, the reaction rate or the kinetics is more sluggish, much slower than the negative electrode. This means I try to make an electrode more active, put some catalyst, or make an electrode more rough, so increase the electrode area to compensate the slow reaction kinetics. Actually, you can see from here. If you try to improve the negative electrode, not change too much, because the key button neck is on the positive electrode over here. So there's several applications for the polarization curve or the implementation for the polarization curve.